Supernovae represent one of the most dramatic and influential phenomena in the cosmos, marking the explosive deaths of massive stars while simultaneously seeding the universe with the building blocks necessary for future stellar generations. These cataclysmic events play a pivotal role in stellar evolution, not merely as endpoints for certain classes of stars, but as critical mechanisms that drive the chemical enrichment of galaxies and trigger new cycles of star formation. The process by which massive stars conclude their nuclear fusion cycles and collapse creates conditions of extreme temperature and pressure that cannot be replicated elsewhere in the universe. Through violent explosions that can briefly outshine entire galaxies, supernovae disperse newly synthesized heavy elements into interstellar space, providing essential materials for subsequent generations of stars, planets, and eventually life itself. The path to a supernova begins with the formation of a star from collapsing clouds of gas and dust within nebulae or molecular clouds. While all stars follow similar early evolutionary paths, their ultimate fate depends critically on their initial mass. Stars with masses approximately 10 or more times that of our Sun follow a dramatically different evolutionary track than lower mass stars like our Sun. These massive stars burn through their nuclear fuel at a tremendously accelerated rate, remaining on the main sequence for only a few million years compared to the billions of years expected for stars like our Sun. During this main sequence phase, massive stars fuse hydrogen into helium in their cores, generating the energy and pressure necessary to counterbalance the inward pull of gravity. As massive stars begin to exhaust their core hydrogen, they undergo a series of evolutionary changes that ultimately lead to their explosive demise. Unlike smaller stars that eventually become red giants, very massive stars evolve into red supergiants, expanding to enormous proportions as they begin fusing heavier elements in their cores. These stellar behemoths can reach diameters hundreds or even thousands of times that of our Sun. During this phase, the star develops a layered structure, with the heaviest elements concentrated at the center and progressively lighter elements arranged in concentric shells outward. The core progressively fuses helium into carbon, carbon into neon, oxygen and magnesium, and continues this process of nucleosynthesis to create increasingly heavier elements. The crucial distinction between low-mass and high-mass stellar evolution emerges in the types of fusion reactions that can occur. While lower-mass stars typically only fuse elements up to carbon before electron degeneracy pressure halts further reactions, massive stars can continue the fusion process to create even heavier elements. In the cores of the most massive stars, fusion reactions proceed all the way to iron. This represents a fundamental turning point in stellar evolution, as iron fusion does not produce energy, but instead consumes it. When the star has developed an iron core, it reaches a critical juncture where nuclear fusion can no longer generate the energy needed to counteract gravity's relentless inward pressure. When fusion reactions in the core of a massive star can no longer continue, a catastrophic chain of events unfolds with astonishing rapidity. The iron core, no longer supported by the energy from fusion reactions, collapses suddenly under the immense gravitational pressure. This collapse occurs at approximately 1/4 the speed of light, transforming the core from a diameter of several thousand kilometers to merely tens of kilometers in less than a second. The collapsing core reaches densities so extreme that protons and electrons are forced to combine, forming neutrons and releasing a massive surge of neutrinos in the process. These neutrinos carry away enormous amounts of energy, briefly containing more energy than all the visible light in the observable universe. As the core collapses to form either a neutron star or, in the case of the most massive stars, a black hole, the outer layers of the star fall inward only to rebound violently off the newly formed ultra-dense core. This rebound, coupled with the intense neutrino flux, generates an outward-moving shockwave of unprecedented power. The extremely energetic neutrinos produced during core collapse fragment some atomic nuclei in the surrounding stellar material, releasing neutrons and additional energy that further augments the developing shockwave. The intense heat and pressure generated by this shockwave trigger rapid nuclear fusion in the star's outer layers, creating a spectrum of heavy elements in mere seconds that would take billions of years to form under normal stellar conditions. Supernova nucleosynthesis represents one of the most significant processes in the universe for creating and distributing heavy elements. During the explosive phase of a supernova, multiple nucleosynthetic processes occur simultaneously under extreme conditions that cannot be replicated elsewhere in nature. In massive stars, the sequential burning processes of helium, carbon, oxygen, and silicon during their normal lifetimes produce primarily alpha nuclei, elements whose atomic mass numbers are multiples of 4, such as carbon-12, oxygen-16, and neon-20. These elements form through the successive addition of helium-4 nuclei, building progressively heavier elements. The explosive nucleosynthesis that occurs during the supernova itself dramatically extends this process. When the shock wave from the collapsing core propagates outward through the star's layered structure, it creates temperature and density conditions that rapidly accelerate nuclear reactions. The sudden temperature spike causes explosive burning that synthesizes non-alpha nucleus isotopes more effectively than the previous hydrostatic burning processes, creating a diverse array of elements. Supernovae are particularly significant for creating elements between oxygen and rubidium in the periodic table. Additionally, the extreme neutron-rich environment in a supernova enables rapid neutron capture processes, known as the IR process, which builds many of the heaviest elements in the universe. Elements heavier than iron cannot be produced through standard fusion processes that power stars, as these reactions would consume rather than release energy. Instead, the production of these heavy elements requires the enormous energy and neutron flux available only in supernovae and neutron star mergers. During the supernova explosion, some of the lighter elements created during the star's lifetime capture neutrons released in the explosion, forming heavier than iron material, including various radioactive elements. These newly synthesized elements are violently ejected into space, enriching the interstellar medium with metals that will eventually be incorporated into new stars and planetary systems. Supernovae exert profound influence beyond their immediate stellar neighborhood, playing crucial roles in galactic evolution and star formation regulation. The explosive energy from these events drives powerful winds that can expel significant portions of gas from galaxies, particularly from smaller dwarf galaxies with weaker gravitational wells. For instance, a galaxy with a circular speed of approximately 50 km/s can lose 60 to 80% of its gas over a timescale of about 1 billion years due to supernova feedback. Even larger galaxies like our Milky Way might have lost as much as 20% of their mass through supernova-driven winds. This process of removing gas affects the efficiency of future star formation and helps shape the evolution of galaxies over cosmic time. The interaction between supernovae and their surrounding environment displays remarkable complexity. Recent simulations have revealed that when a supernova explodes within its natal molecular cloud, it does not uniformly affect the entire cloud. Instead, the explosion finds and exploits existing weak points, creating channels through which the energy can escape, while leaving much of the well-shielded dense gas largely unaffected. This channeling effect becomes more pronounced when previous stellar feedback, such as ionizing radiation and stellar winds from the progenitor star, has already created pathways through the cloud. Through these pre-established channels, the supernova's energy can more effectively escape to impact the larger-scale galaxy, carrying less mass but retaining more of its kinetic energy. Supernovae complete and reinitiate the cycle of stellar evolution by dispersing heavy elements and triggering new episodes of star formation. The outer remnants ejected during a supernova form new clouds of dust and gas, creating nebulae that serve as nurseries for the next generation of stars. These nebulae are enriched with the heavy elements synthesized both during the massive star's lifetime and during the explosive nucleosynthesis of the supernova itself. When gravity causes these enriched clouds to collapse, forming new stars and planetary systems, they incorporate these heavier elements, creating increasingly metal-rich stellar populations. Supernovae stand as cosmic linchpins connecting stellar life cycles, galactic evolution, and the chemical enrichment of the universe. These spectacular explosions mark both an end and a beginning in the story of stellar evolution, the death of massive stars, and the birth of the conditions necessary for new generations of stars and planets. Through the synthesis and dispersal of heavy elements, supernovae provide the essential building blocks that make complex chemistry, planets, and ultimately life possible. Their energy output regulates star formation on galactic scales, while their nucleosynthetic yields establish the chemical composition of future stellar generations. Far from being merely destructive events, supernovae represent one of nature's most powerful creative forces, driving the ongoing evolution of stars and galaxies throughout cosmic history.